In this video, we'll develop the linear regression technique for curve fitting. After studying this video, you should be able to understand how the linear regression algorithm fits a line to a data set. You should also be able to calculate and interpret some statistics quantities that measure the quality of a linear fit, and use MATLAB's polyfit function to fit a linear equation to data. So, the basic goal of a linear fit is given some data, probably from an experiment or a study, to fit the equation of a line, to find the coefficients of equation of a line that can model that data. So if we think about a line as being a0 plus a1x, where a0 is the y-intercept and a1 is the slope, and what we want to do is find those coefficients that gives us the best fit of the line. Now we can visually see that this is a pretty good fit right here, but the basic idea what we are going to do is minimize the total error between our model and the data. So first we have to think about how are we going to measure that total error. And so what we'll do is actually define the residuals. And so this will be the residual here will be the distance, call that E sub I, and that'll be the distance from the ith data point, which is y sub I, minus what the model predicts for that ith data point, which would be a0 plus a1 times x sub I. And since we have multiple data points, we want to have a measure for all of the data points. So the way to do that is we will sum them up. But since some of them might be positive and some of them might be negative, depending on whether the data point falls under the line or over the line, so that they don't cancel each other out, we will square them. And we're going to call that quantity SR, or the sum of the squares of the residuals. And you might notice also, if you recall from our discussion of matrix algebra, that this looks very similar to the Euclidean norm of the residuals. It's actually the square of the Euclidean norm of the residuals. And we're just going to minimize that. So let's look at how we can do that. So if we take that equation now, SR is the sum of, here's our residual. There's the ith residual. Plugging in our linear equation, notice what it looks like here is very similar to the term in the variance, except for the difference for the variance from the statistics video that we're looking at the residuals with respect to the mean. So another way to think about what we're doing is we're minimizing, recall that the variance is a measure of spread, we're minimizing the spread of the data about our model by taking this approach. So what we need to do now is solve for a0 and a1, the values of those that minimize this quantity. And to do that, we'll take the partial derivative with respect to each and set those equal to 0. And this becomes a linear 2 by 2 system. And so we would know how to solve that, and go ahead and solve it. Although we're not going to take this much further because this isn't actually how MATLAB performs a regression, but it does get at the basic idea of linear regression. And let's talk about a few cautions here. There are some very important implied statistical assumptions that we've made in this technique. One assumption we've made is that there is no error in the x data, or we could be close to that assumption if the uncertainty in x is much, much less than the uncertainties in y. And that's often the case for an experimental setup where you have a lot of control in terms of x, which is your independent variable, but you're measuring the resulting y values, and you might not have as much control. You're likely to have more uncertainty there. So the consequence of this is we can't simply reverse it. The regression of y versus x is not the same as the regression of x versus y. Another implicit assumption is that the y values are independent of each other, so the y values don't influence each other in the data set. And if we took enough y values at a given x, they would be normally distributed. So recall that normal distribution here, the bell curve about some mean, call that y bar sub I, would be the mean y value at a given x sub I. And given enough data points, each y value would be normally distributed at that data point. So just keep those in mind whenever you're applying this curve fitting algorithm. So once we've calculated our coefficients, one thing we'd like to do is evaluate the quality of the fit. One measure we can use to do that is called the coefficient of determination. And the coefficient of determination, or the r squared value, is defined as st minus sr divided by st, whereas st is the sum of the squares of the residuals with respect to the mean, and SR is the sum of the squares of the residuals with respect to that model. Now this is a generally applicable measure of the curve fit even as we move forward into some nonlinear curve fitting techniques. R squared represents the percentage of the original variation in the data that is explained by the model. So if we had a perfect fit, that means that SR would be 0 and R squared would be equal to 1. So if R squared is close to 1, we have a good fit. Or that's one indication of a good fit. If R squared equals 0, there's no improvement over simply picking the mean. If R squared is less than 0, our model is actually worse than simply modeling the data by taking the mean or the average of the data. So qualitatively, what the coefficient of determination is doing is comparing how well does our model, our curve fit, explain the data compared to how well does it explain the data to just take the average value. Another measure of curve fit quality is called the standard error. This is similar to the standard deviation. Recall the standard deviation from the statistics video. So again, though, in the standard deviation, now that we've introduced st, that would be the square root of st over n minus 1 is the standard deviation. The standard error, we're going to assume that the residuals are normally distributed about the model, which is a reasonable assumption that follows from that assumption that the data would be normally distributed at any given x value. Then we can define the standard error as the square root of SR, where SR is now the sum of the squares of the residuals with respect to the model, divided by n minus 2. And notice the difference here. In standard deviation equation, this is n minus 1. Recall that that is the number of degrees of freedom in that model. In that case, the mean of the data has 1 degree of freedom because it's just a constant number. Now we have 2 degrees of freedom. So the equation changes a little bit, and those degrees of freedom would be A0 and A1. And you can think of those degrees of freedom as those are the two model coefficients, and they're almost like knobs that we're turning to tune the mathematical model to the data. And that's kind of where that term degree of freedom comes from. So the standard error represents the confidence interval for how well the model predicts the data. So one way to think about that is here's some data modeled by some average y bar, and Y bar is going to, the data is going to have some distribution of the residuals, about the residuals. This is a distribution of the residuals, and those are going to be distributed about Y bar, so those are the Y sub i's minus Y bar, according to roughly a normal distribution, and that would be the standard deviation would define the shape of that normal distribution. Now, if we fit a line through the data, and now we can look at a distribution of the residuals E sub I or yi minus y model, where the model is our linear equation evaluated for each data point, we have a much tighter bell curve, and the shape of that bell curve is defined by the standard error, SYX. And if you recall, what we're saying there is that our model then would predict 95% of the data yi within twice that standard error. Another thing you can do with a curve fit, and something that you have to do and always keep in the back of your mind, is to look at qualitative measures of the fit. So that's just how does it look, how does it fit through the data, and also maybe plotting the residuals is a good thing to look at. Do those residuals appear to be randomly distributed about the model? So here's an example. This is going to have an r squared value that's going to be very close to 1, probably greater than 0.95. So a very good r squared value for this curve fit. But if you do a plot of the residuals, and you can kind of see there's a pattern to the data on the first plot, but if you plot the residuals, you'll see there's clearly a periodic pattern in the data here. And when we see that, that tells us there might be some functional variation in the data that the model is not capturing. Maybe if this is some physics experiment and this periodic variation, that could be something like electrical noise in our data acquisition equipment. So if we wanted to try and model that noise, we can, but we need to use some model functions that aren't linear, and we'll talk about how to do that in following videos. But first, let's talk about doing linear fits in MATLAB. The way to do linear fits in MATLAB is to use the built-in function polyfit, and that determines the coefficients for a least squared fit, actually of an nth order polynomial to data. So for a linear fit, we would say n equals 1 for a linear fit. And that polyfit function is more general and can do any order polynomial. We would input the x is the independent data, y would be the dependent data, n again is the order of the fit, and the output is a vector of polynomial coefficients, and this vector behaves similar to the vectors for defining polynomials that we looked at earlier with the roots function. And you can use the polyval function to directly evaluate the predicted data points from your model. P would be your coefficient vector, and x would be the points you want to evaluate it at. And that can be a vector of x values. Polyfit command actually doesn't do linear regression. It uses a general linear least squares approach that we're going to talk about in a future video. But nonetheless, if you want to perform a linear fit in MATLAB, polyfit is the easiest way to do it. And we'll see an example of how to use polyfit in the next video.